Welcome to this video on viscosity and viscous stresses. What we're going to do today is talk, well, first of all, we're going to introduce the concept of viscosity. It's a fluid property, it's an important one. And then we'll discuss some various aspects of fluid viscosity. Then we'll talk about how you calculate viscous stresses. These are tangential stresses acting on a surface. We've already talked about hydrostatic pressure forces or hydrostatic pressure that would act normal to a surface. Viscous stresses act tangential to a surface. So we're going to talk a little bit about how you would calculate those. So let's first of all look at the screen here. You'll see on the screen we have a picture of a funnel with some black, it's actually pitch in here. It's kind of like a tar substance. And it's highly viscous. We'll talk about what we mean by viscosity a bit later. But this is you'll see that this pitch in the funnel is slowly dripping out. You can see kind of a drop that's forming here and then some drops that have already landed in the beaker down here. The whole thing's contained in a bell jar just to keep the atmospheric, any sort of breezes or things like that from interfering with the experiment. This is actually the world's longest running experiment. It's in the Guinness Book of World Records. It was started in 1927 by a professor at the University of Queensland. He just wanted to demonstrate to students that pitch, which it's like hard tar. If you held it in your hand, it would be like a solid, but it actually has viscous-like properties. It's just over very long time scales. So in 1927, he put this pitch in this funnel, and then he first of all let it sit there for 3 years before opening the exit of the funnel. He just wanted it to kind of flow and fill up into the funnel. And then after 3 years, he cut open the exit of the funnel and then just let it drop out, drip by drip. But when I say that, it takes a very long time for a drop to happen. Apparently, since 1927, I guess really 1930, since that's when he opened it up, as of 2014, there were only 9 drops of pitch that have come out of there. So it's taken such an enormous amount of time. What is that? That's 84 years to get 9 drops of pitch to come out. Based on that, you can estimate the viscosity of the pitch, and it's something like 230 billion times more viscous than water. That's 230 billion with a B more viscous than water. The amount of pitch that's in that funnel, that's remaining in the funnel, means that the experiment probably will last for about another 100 years before it's completely emptied. And if you are really interested in watching it, it's actually televised. There's a live stream from the University of Queensland in Brisbane, Australia, where this is. And they have a webcam aimed at it. And if you look at the screen here, there's a little web address here for the live stream. If you like watching really boring things, you can go there and take a look at it and just sit there and wait until another drop falls. You better be very patient because it takes a long time. So kind of a fun little experiment just to introduce us to the concept of viscosity. So let's go ahead and get into it. So the quantity of viscosity is a fluid property, as I mentioned. It's really kind of a measure of the internal friction of a fluid. You've all probably heard of viscosity before and you have some feel for it. You know that honey is more viscous than water. But what that really means is that there's an internal friction to the fluid that resists the movement of the fluid, and that internal friction is related in some way to the viscosity. We have different kinds of viscosity. Let me talk about that first, and then I'll get back to this idea of internal friction. So first of all, when we say viscosity, we generally mean what's known as dynamic viscosity. And we'll give it the symbol mu. So I'll either say dynamic viscosity or viscosity. They mean the same thing. And this viscosity has, just to give you some common dimensions and units, so the dimensions of viscosity would be force times time over length squared. And so common units would be like a Newton second per meter squared, or that can be rewritten as a Pascal second. So that's a very common unit used for viscosity, Pascal seconds. In English, it would be English units would be pounds 4 seconds per square foot. That's less common. Another very common unit is a poise, and that's 10 poise, or poise, that's another way to say it. 10 poise is 1 Pascal second. And 1 centipoise, which is another common unit, it's just 1/100th of that, of course. 0.01 poise, or 0.001 Pascal second. You might ask yourself, why do we care about a centipoise? And the reason for that is because water has a dynamic viscosity of 1 centipoise. So it's a convenient unit to remember. So let me get back to this idea of the internal friction and viscosity being related to that. So imagine we have some velocity profile in a fluid. So we'll say this is the x velocity and this is the y direction. If we zoom in on a narrow range of that, let's say 2 different layers of fluid. So let's say this little layer of fluid corresponds to this one, and then we have another layer of fluid here. You'll see that one layer of fluid is moving a little bit faster than the other. So let's say the bottom layer of fluid is moving at velocity ux, and then the velocity of the little piece of fluid above it is moving a little bit faster, ux plus dux. And then the difference in height between these two would be dy, just a small distance. So the velocity gradient, which is just how the velocity changes with respect to y, would be dux dy. That's how the velocity changes as you move in the y direction. It's just this little bit of change in velocity over the change in height. That's what we call the velocity gradient, just how the velocity changes in some particular direction. Well, it turns out that the shear stress you'd have to apply, let me just draw a shear stress on here. Let's say I apply some shear stress on that top piece of fluid to get it to move off to the side relative to the bottom. That shear stress I'll write as a symbol tau for shear stress. And I'm going to say that it's acting on the y face in the x direction. Now if you've had a strength of materials course, you're familiar with the sign convention for stresses, but if you haven't, let me just take a little aside here to talk about that. So when we talk about stresses, let me draw it in a little cube here. When we talk about stresses, there's a certain sign convention we use. So let's put an xy coordinate system here. So if I draw a positive shear stress on this upper face, that's a positive tau yx stress. This first subscript, the y, tells me which face the stress is acting on. What I mean by that, it's the face with a normal, a unit normal vector pointing in that particular direction. So on that particular face, the unit normal direction n hat here is pointing in the y direction. So the first subscript indicates the face that you're on. If I was on this side face here, and I was drawing a shear stress on this one, it would be start with a tau x something. This is actually a tau xy stress. So the first subscript is what face you're on. The second subscript tells you the direction that the stress is pointing in. So you'll see here on this top part, it's on the y face pointing in the x direction. You can see that. It's pointing in the x direction there. The one on the side here, it's on an x face because the normal is in the x direction, and it points in the y direction. It points upward in the y direction. So the sign convention for stresses is if you're on a positive face, meaning the normal vector is pointing in the positive direction, like right here at the top, a positive stress on a positive face points in a positive direction. So this shear stress is on a positive face, and a positive shear stress would point in the positive x direction. If I'm on the bottom, this would be a negative face because the normal vector is in the negative y direction. So a positive stress on a negative face points in the negative direction. So down here, this stress is again a tau yx stress, and I've shown it here as pointing in it being a positive shear stress on the negative face, because positive stress on the positive face points in the positive direction. A positive stress on a negative face points in the negative direction. So again, you've probably heard that from strength of materials. If you haven't heard that yet, you will. It's just the sign convention that we use for stresses. Okay? So getting back to our situation, on this little piece of fluid, this would be a positive tau yx stress. It's on the y face because the normal vector would be in the y direction, and it's pointing in the x direction, so like the ux direction here, and so it's pointing that direction. So it turns out that shear stresses are a function of the velocity gradient in fluids. So I'll just write that here. So we know tau yx is some function of dux dy. So it's some function of that. You can think about like a spring, like a solid material behaves like a spring. The stresses that it takes to deform that solid material are related to the deformation of the material, right? This is like a spring. The force required to pull a spring apart depends on how much you deform the spring. That's true for solids. When you deal with liquids, the force that's required to move the fluid is related to the velocity gradient. Not how much you deform the material, but it's just it's related to the velocity of the material and how the velocity changes between neighboring bits of fluid. So our shear stress in a fluid is related to the velocity gradient. Now, what is that function? Well, it turns out for different fluids there are different functions. But one very common type of fluid, known as a Newtonian fluid, has a proportionality between these two things. So for a Newtonian fluid, that function is just a proportionality. So tau yx is proportional to dux dy. And let's just put a constant of proportionality in there. And we'll call that constant of proportionality a mu here. That constant of proportionality is actually the viscosity. That's where the viscosity, that's how the viscosity is defined. So for a Newtonian fluid, the shear stress is proportional to the velocity gradient. It's a special class of fluids. Not all fluids behave that way. But for Newtonian fluids, the shear stress is proportional to the velocity gradient, and that constant of proportionality is the dynamic viscosity. So that's where the dynamic viscosity comes from. So you can see that how hard you have to shear the material. You know, if you shear it very hard, you have a high shear stress, you'll end up with a large velocity gradient. You'll get a lot of movement in the fluid, right? If you have a higher viscosity, you won't get as much movement to the fluid, like honey, right? If you apply a large stress to cold honey, it doesn't move that much because it has a very high viscosity. The velocity gradient is small. So these are known as Newtonian fluid. This is a Newtonian fluid behavior. Now, why do we care about Newtonian fluids? Well, it turns out that water and air are both examples of Newtonian fluids. The two most common substances we deal with in engineering, water and air, are both Newtonian. And there are other fluids that behave in a Newtonian manner as well. So that's very convenient for us. Now, fluids that don't behave like this are called non-Newtonian. So it's like you have elephants and non-elephants, right? You have Newtonian fluids and non-Newtonian fluids. But fortunately for us, we have water and air are both Newtonian, and it's relatively easy to work with those fluids compared to non-Newtonian fluids. So this is an important point to keep in mind, is that for a Newtonian fluid, the shear stress is equal to the dynamic viscosity times the velocity gradient. We're going to use that frequently in this course. So let me just talk a little bit more about Newtonian versus non-Newtonian fluids. So I have a plot here showing the shear stress as a function of the rate of shearing strain, or this is just the velocity gradient. In fact, let me just cross that out. It's not incorrect what I've said there, but it's just easier for me to just write velocity gradient. So this is dux dx, and this is shear stress tau yx. So we just said that for a Newtonian fluid, they're proportional to one another, and that proportionality is the dynamic viscosity. I'll just write it as mu there. So we've just talked about Newtonian fluids. So shear stress, velocity gradient for Newtonian fluid, they're proportional, and that constant of proportionality is the dynamic viscosity. Now, there are many different kinds of fluids with different kinds of behavior. I'll just show you two different kinds here. First one is a non-Newtonian shear thickening fluid. So that's this curve down here. So you'll see here that the larger the velocity gradient, the larger the shear stress becomes. So if we look at the local slope, like right at this point, let's call that the apparent viscosity. So it's like the viscosity just at this local point. You'll see that the apparent viscosity gets larger. Right? So the apparent viscosity at 2 is larger than the apparent viscosity at 1 down, down at this point here. So as you increase the velocity gradient, the fluid becomes more viscous. Now, we've all probably dealt with a fluid like this before. If you've, in high school and such, it's a cornstarch water mixture. Cornstarch and water, when you put them together, behaves in a non-Newtonian manner, and it's a shear thickening kind of fluid, similar to what I showed here. So, one example of this then is cornstarch and water. Sometimes it goes by the name oobleck. If you take that cornstarch and water mixture and you have it in your hand and you just let it sit there, it'll just kind of ooze out of your hand. It behaves like a liquid because it has a low viscosity, and it just flows. But if you squeeze it really quickly, so you have a large velocity gradient, you squeeze it fast, it behaves like a solid. It has very high viscosity. Right? So it behaves like a solid like that. There's some great videos available on the internet that you can take a look at where people fill up swimming pools with cornstarch and water, and if you just step into it slowly, you'll sink down. But if you try to run across the surface, it's like running across a trampoline. It can support the weight because it behaves more solid-like. So there are videos of people running across swimming pools. I saw one where a person was trying to ride a bike across the swimming pool. He was unsuccessful because he couldn't ride a bike to begin with. But anyway, it was kind of fun to watch. And people doing all kinds of weird things with cornstarch and water mixtures. So that's a good example of a non-Newtonian shear thickening fluid. Now there's another kind that I'll talk about, and that's the curve here. This is a non-Newtonian shear thinning fluid. Here you can see that the apparent viscosity at point 1 is larger than the apparent viscosity at point 2. So the more you shear the material, the easier it flows. Now an example of this would be paint. If you take paint and ideally, if you dip it into the paint bucket and you pull it out slowly, it'll drip a little bit, but you don't want it to all fall right off your paintbrush right away, right? You want most of it to stay on your paintbrush. But then when you go to paint the wall and you slide the paintbrush against the wall and you're starting to paint it, you want the paint to flow very smoothly and onto the surface. So it actually is designed to be shear thinning. So when you start to paint with it, it flows easily. When you get it out of the paint bucket, it doesn't flow much at all. Or not as well. So that's an example of a shear thinning fluid. Another one we all have experience with is blood. So blood is slightly shear thinning. And this kind of makes sense evolutionarily speaking. You can imagine that cavemen are running around being chased by saber-toothed tigers. Those cavemen whose hearts didn't have to work as hard when they were running fast, and the blood vessels were constricted and they were, the heart was pumping very hard, trying to get away from the saber-toothed tiger. If your blood was a little bit shear thinning, it'd be easier on your heart to pump it through your body because the viscosity would be a bit lower. Those cavemen that had shear thickening blood or maybe just purely Newtonian blood wouldn't be as successful, and then they'd be dinner for a saber-toothed tiger. So blood turns out to be a little bit shear thinning. Not a lot, but just a little bit. So there's a whole area of study for the behavior of fluids with respect to the velocity gradients, and that field of study is known as rheology. And there are many, many other types of non-Newtonian fluids, some that behave like springs and some other weird kinds of behavior. But it's stuff that we're not going to cover in this course. We're going to cover only Newtonian fluids for the course. But rheology is fascinating and lots of interesting things there. So if you go on to higher level fluid mechanics, there's some really cool stuff that people have been looking at with different rheologies of fluids. All right, let me move on here. So let me show a plot of what the viscosity looks like as a function of temperature. So on this axis, the vertical axis, we have, they call it absolute viscosity, but it's the dynamic viscosity, mu. So this is a logarithmic scale on the vertical axis, so viscosity over here. And then on the horizontal axis, we have temperature. So temperature down here. And what you'll see is down at the bottom, we have the viscosities of gases, various gases. So for gases, if you increase the temperature, the viscosity goes up a little bit. Okay, so you can see that down here at the bottom. But when you deal with the liquids and you increase the temperature, the viscosity goes down. You can see that very strongly up here with all of these various curves. These are all liquids, and you can see water here. The viscosity decreases as you get to higher temperatures. Again, if you have any experience with honey, like you're making tea or something, if your honey's stored in a cold space, it doesn't flow very well. Once you get it into the cup of tea that's hot and you start mixing it up, it flows very easily. It's because the viscosity is changing with temperature. You also see it in car commercials all the time. They're talking about oil. You know, what kind of oil do you need for your car engine? You want to make sure the viscosity is correct when as the temperature of your engine goes up and such. Again, the viscosity of oil decreases as temperature goes up. So you have to take that into account when you design automotive oil. And just to give you some typical numbers here. So the viscosity of water at kind of room temperature, 20 degrees C, is 1 centipoise. Just what I had kind of talked about before. The viscosity of air at the same temperature is quite a bit smaller. It's much smaller, 0.018 centipoise. Right? So it's the dynamic viscosity of water is much higher than that of air. Kind of what you'd expect. Now there's another kind of viscosity. I mentioned it a little bit earlier. There's another kind of viscosity that we deal with, and it's called the kinematic viscosity. We'll give it the symbol nu, and it has dimensions of length squared over time. So the typical kinds of units would be like square meters per second or square feet per second. And it's defined as the dynamic viscosity over density. Okay, so when we want to talk about kinematic viscosity, I'll typically say the word kinematic viscosity. If I just say viscosity, I mean dynamic viscosity. If I want kinematic viscosity, I'll say kinematic viscosity. Why do we have these two different kinds of viscosity? Well, it turns out that grouping of terms, mu over rho, is very common in fluid mechanics. So it's convenient just to give it its own symbol. It just shows up all the time. You'll see that later in the course, that grouping of terms. So we just give it a special name, call it kinematic viscosity. It actually has a more fundamental meaning. It turns out it has units of diffusion, like a diffusion constant. It has to do with the diffusion of momentum out into a flow. But that's a more advanced topic. We don't have to worry about that here. But just be aware that kinematic viscosity is another kind of viscosity that we'll be using later in the course. We won't use it much at the beginning, but we'll use it later. So just to kind of give you a feel for values for kinematic viscosity. Oh, by the way, one other kind of unit I should have said for kinematic viscosity is the stoke. So 1 stoke is 1 square centimeter per second. By the way, Pause and Stokes, those are, again, famous people who were involved with fluid mechanics back in the day. And so we give them, units, we name units after them just to kind of honor their contributions. So the kinematic viscosity of water at room temperature is 1 centistoke. And the kinematic viscosity of air is about 15 centistokes. So one interesting thing here is you'll see the dynamic viscosity of water is much higher than the dynamic viscosity of air, but the kinematic viscosity of air is much higher than the kinematic viscosity of water. It has to do with differences in density. That water is about 1,000 times more dense than air. So the differences in density give rise to the differences in the kinematic viscosity. Okay. So I've talked a little bit about the property of viscosity, talked a little bit about kinematic viscosity. Let me show you a little bit how we use it. Okay, and to motivate this, I'm going to use a common engineering model for a flow. This is called a Coop Flow. It's shown on your screen here. Again, named after a famous person in fluid mechanics. So a Coop flow looks like what you see on the screen here. It's two parallel plates. They're infinitely long, so they go on forever from side to side and front to back. The bottom plate is fixed, and the top plate is moved at a constant speed off to the side. You can see that here. Bottom plate is fixed. The top plate moves at a constant velocity off to the side. And we're going to fill, between those two plates, we're going to fill it with fluid. We're also going to separate the plates by a distance h, which is fixed. So we just have a fixed distance between them. We'll say that there's no pressure gradient involved in the x direction. So that just means the pdx is 0. There's no change in pressure in the x direction. The reason we do that here is because this is just the way a Coop flow is defined. There are different ways you can get fluid to move. Okay, one way you can get fluid to move, as we'll show in this example, is you can move a boundary. It turns out fluid sticks to a boundary. That's called the no-slip condition. We'll come to that in a moment. So you can move a boundary, and that causes fluid to move. Another way you can move fluid is you can change the direction of gravity. So if I had water in a container and I tipped it, gravity would act, in a different orientation relative to the fluid, and it would cause the fluid to move, right? So changing gravity or using gravity, moving a boundary, both are ways to get fluid to move. A third way to get fluid to move is to apply pressure gradient. If I push on one side a little bit harder than I push on the other side, so if I have fluid in a container and I apply a larger pressure to this side than on this side, I'll get a pressure gradient. The pressure changes from one location to the other, and then I can push the fluid through the pipe. So a pressure gradient's a third way to get fluid to move. For a Coop flow, we're only going to move the fluid by moving the boundary. We're just arbitrarily choosing this geometry to study. Okay, there are other geometries where we use pressure to get the fluid to move and so on, but for this one we're just going to move the boundary. So this is called a Coop flow. All right. So first of all, why do we have this kind of idealized geometry? It seems very artificial. Why do we care about this? Well, it turns out it's a very useful model for many engineering situations. Engineering deals with approximations all the time. We almost never model anything perfectly. In fact, we never model anything perfectly. That would require quantum mechanics and so on. We always make approximations. So the Coop model is an engineering approximation for real life. For example, let's imagine we have a car driving along on a wet road, and we have smooth tires, slick tires without any treads on them. So it's just a smooth tire, and there's a layer of water on the road. This is obviously not to scale. If you had that much water, you'd be in a lot of trouble. So anyway, let's say the car is moving along this way. If we zoom in on this kind of region where the tire is, so let me kind of zoom in on this. So here's the tire. The tire is not perfectly round. It kind of flattens out at the point of contact. So this is the tire. And let's say you hit your brakes and you start to hydroplane, right? You're driving along, you hit this water, and you're starting to lose control. You slam on the brakes. You don't have any analog brakes, and the tire locks up. You start to slide along, hydroplaning on the surface of this water. That's what we're showing here. So the tire is moving in this direction at velocity v. The ground, of course, is fixed, and you have some water in here. Well, this region, in this kind of dashed region here, looks pretty close to this Coop flow off to the side. So we could approximate the behavior underneath the tire in that small region as being a Coop flow. It's an engineering model. It's not exactly a Coop flow, but it's a pretty good approximation. So we do this kind of thing all the time. So that Coop flows are useful for basic understanding, but they're also useful engineering models. It's a useful engineering model as well. Okay, so I've gone too far there. So here we have our Coop flow, and I've drawn the velocity profile of the fluid inside between the two plates. Now, I'm just giving you this velocity profile. It's a linear velocity profile, v over h times y. So when y is equal to 0, the velocity is 0. So down here, the velocity is 0. And when y is equal to h, right up here, the velocity is v. It's the same as the plate. So for now, I'm just giving you the velocity profile. Later in the course, we'll actually derive it. And you'll see that we don't have to assume it. It'll actually be something we can derive. But for now, we'll just assume it. So a couple of things I just highlighted. first of all, the velocity at the bottom is 0, which is the same velocity as the plate. And the velocity at the top is capital V, which is the same velocity of the plate. This is what we call the no-slip boundary condition. No-slip boundary condition, all abbreviated as BC. It just means that fluid sticks to the boundary. So the fluid at a boundary will have the same velocity as the boundary. We see this experimentally all the time under ordinary engineering situations. When you start to deal with special situations like in the upper atmosphere where the molecules are separated a long distance from one another because there's very little air in the upper atmosphere, and so the molecules are well separated. Up there, the no-slip boundary condition doesn't really hold. Same sort of thing if you get into really microscale, microfluidics, very small dimensions, tiny, tiny dimensions, things less than a millimeter in size, dealing with microns in size. There, the no-slip boundary condition also doesn't hold necessarily. But for the vast majority of engineering applications, the no-slip boundary condition holds. We just see it experimentally. So that's a very common boundary condition that we'll be using. So you can see in this velocity profile that it satisfies the no-slip boundary condition right away. So now that we're given the velocity, and by the way, this is the velocity in the x direction, just using our coordinate system. So now that we have the velocity profile, we can actually calculate the shear stresses in this particular flow. So we know that tau yx, the shear stress on a y face acting in the x direction on a fluid element, is mu times dux dy. And I can go ahead and substitute in for my velocity. If I look at my velocity here, when I take the derivative with respect to y, it's just going to be v over h. So in this particular case, the shear stress on the little bits of fluid are all constant. Everywhere you look on there, you get the same shear stress. It's mu times v over h. And so that'll be the same shear stress on a fluid element right up here at the top, as well as a little fluid element down there at the bottom. In fact, if you look at the picture at the bottom here, I just kind of show positive shear stresses acting on the fluid. Let me highlight those in yellow. So here is the positive shear stress acting at the fluid on the top. Here's a positive shear stress acting on the fluid at the bottom. On the top, what's happening is the plate is pulling the piece of fluid along with it to move with the plate. And on the bottom, the wall is holding the fluid back so it doesn't move, so it sticks and stays stationary. And from Newton's third law, we know that we'll have equal and opposite forces acting on the walls. So let me highlight those in kind of this pink color. So on the top, that little pink stress that I highlighted there is the stress acting on the wall that the fluid is exerting on the wall. So the wall is wanting to be held back by the fluid. So in order to move the wall, I'm going to have to apply the shear stress off to the side to keep it moving, to keep it moving along. If I wanted to get the force, the shear force, I would multiply that shear stress times the area, because remember the stress times an area gives you a force. Right? So now by knowing something about viscosity, we can calculate shear forces. Let me just highlight on the bottom the shear stress acting on the wall down there. This is, again, the shear stress that the fluid exerts on the wall. Down there, what's happening is the fluid wants to pull the wall along, right? Okay. Normally, you can kind of work out the directions of shear stresses just intuitively. You don't have to worry about the stress sign convention so much. You can always go back to the stress sign convention to figure out the direction of the stresses. But 9 times out of 10, you'll be able to do it just intuitively. You can just sort of see which direction it'll be. All right. Now let me talk about a few other things here. Just a couple of definitions. One is a definition of an inviscid flow. We'll talk about this within the course. We'll talk about inviscid flows. An inviscid flow is one that has no shear stresses. So a flow with no viscous stresses. The taus are 0. Okay, so how could we get an inviscid flow? Well, if you look at our equation, let me just highlight it up here. If we look at our equation for the shear stress, one way to make the shear stress zero is to have zero viscosity. Well, typical engineering fluids always have some viscosity. They may be low, but they're never zero. There's only one fluid that I'm aware of that has zero viscosity, a real fluid even, and that's liquid helium. You basically have to get the temperature of helium down so low, very close to absolute zero, it can behave in a very unusual state where it has no viscosity to it. It's the only fluid that I'm aware of that does that. Okay, I'm back. It turns out, from your perspective, there's a little glitch in the video. From my perspective, my camera was full, so I had to stop the video, starting it back up again. Apologize that it's a little glitchy here. Hopefully it won't throw you too much. Okay, I was talking about inviscid flows and saying that that's a common term that we'll use, but real fluids have some viscosity. So how do we get an inviscid flow? Well, when we go back to the equation for viscous stresses here, we just talked about having viscosity be zero. Well, that doesn't really normally happen in normal engineering situations. But we could have the shear stress, the velocity gradient dux dy could be zero. So let me give you an example of one of those kinds of flows. So what if we had a flow that had a uniform velocity profile? One where the velocity is a constant. So here's our y direction. There's our x velocity. Here, there is no change in the x velocity with respect to y. So du dx, or dux dy, is zero. In that case, the shear stress tau yx would be zero. That would be an example of an inviscid flow, one where the velocity gradient is zero or is almost zero. So just a very small velocity gradient would have very small shear stresses. So we could consider those flows as being inviscid. Okay. Now another term that you'll sometimes hear is called ideal flow. An ideal flow is one that's inviscid and incompressible. So inviscid we just talked about. Inviscid just means that there are no viscous stresses. Incompressible means that the density remains constant. So flows with liquids where the density doesn't change, or even gases at low speeds can also be considered incompressible. So an ideal flow is an inviscid, incompressible flow. All right, let me give you some notes here. Some things to keep in mind with respect to viscosity. Number one, an important one, is that the shear stress can vary from point to point in a flow. I used an example of the Coop flow where the shear stress was constant everywhere, but that doesn't have to be the case. That's a very special situation. In general, the shear stress can vary because the velocity gradient could vary from point to point. Remember that the shear stress, tau yx, is mu times du dx. I'm sorry, I have that backwards. Dux dy. And so it depends on what the velocity gradient is. The velocity gradient could change from point to point in a flow, and so therefore the shear stress could vary. So it's probably better that I write the shear stress at some location. Let me instead of writing y, sorry, my email is getting, I'm getting lots of email at the moment, so I just had to mute that. So let me just say tau yx at some location is equal to mu times dux dy at the same location. Okay, it all depends on what the velocity gradient is there. So let me give you an example. Let's say we had a flow between two fixed flat plates. So this is fixed, and this one is fixed. And I have some fluid in between. Let me put a coordinate system here. Here's y and here's x. And let me put a pressure gradient here. So dp dx is less than 0. What that means is that, let's say I'm pushing on the fluid at the left side here. So I've got some pressure here, and it's a little bit larger than the pressure over on this side, P. In fact, let me get rid of that arrow there. So the pressure on the left side is higher than the pressure on the right side. So there's a little extra pressure on the left. Because I have that pressure difference, that pressure gradient, I'm pushing the fluid through the pipe. Okay, remember I talked before about there are 3 different ways to get fluid to move. The Coop flow moved the fluid by moving the boundary. In this flow, I'm moving the fluid by imposing a pressure gradient. And dP dx being less than 0, what that means is the pressure's decreasing as I move in the positive x direction. dP is negative as dx is positive, meaning the pressure is going down as I move forward. That's because I'm getting pushed from behind, from left to right here. So in that situation, the velocity profile looks like a parabola, actually. Oh, by the way, I should mention that I'm going to put the width of this from plate to plate, let me just draw it this way, is, let's call it h. H is the separation distance between the plates. So the velocity gradient in this situation looks like the following. I'm not the velocity gradient, but the velocity. I'm just going to write out the equation for you. Again, later in the course, we'll actually derive this. But for now, let me give it to you. So the velocity in the x direction looks like a parabola. Give it here on the screen. And you can see the dynamic viscosity shows up in there. So if I take the if I want to find the shear stress here, then what I would do is I would take the velocity gradient. Tau yx is mu times dux over dy. So when I work that out, that'll be 1 over 2 times minus dp dx times h minus 2y. So here you can see that the shear stress varies with y. Right? It's not a constant, but it actually varies. At the shear stress at y is equal to 0, for example, the shear stress on the bottom surface, the bottom plate, that would end up being 1/2 minus dp dx times h. And then if I did the shear stress at y is equal to h on the top plate, that'd be 1/2 minus dp dx times, that would be a minus h. Right, same magnitude, they're just in different directions because of the stress sign convention. On both plates, the fluid would be trying to pull or hold back the plates. All right, take that. Let me rephrase that. On both plates, the plates are trying to hold back the fluid, or the fluid is trying to pull the plates along. Okay, that's kind of a more physical way to think about it. The shear stress at the middle, at y is equal to h over 2, would be, let me just think about this, it would be 0, right along the center line. That makes sense because if you look at the center line, right in the middle there, the velocity gradient is 0. That basically it's a vertical line right at the middle, and so the velocity isn't changing with respect to y, just right at the very middle part of that profile. Anyway, it's not so important that you understand that velocity profile and what the equation looks like. My point I'm trying to make here is that the shear stress can vary from location to location. It all depends on what the velocity gradient is. Okay, so don't think that the shear stress is always a constant. It's not. It depends on the velocity gradient. Okay, that was note number 1. Number 2 is I've written the shear stress just as being like tau yx equals mu dux dy. It's actually a little more complicated than that. The real relationship between the velocity gradients and the stresses looks like this. I'll write it as tau ij is equal to mu times dui dxj plus duj dxi, where the I in the j could just be x, y, and z. So I'll put that over here. So like I and j are kind of like, or let me write it this way. I or j could be x, y, or z. So for example, if I want tau, oops, that's not what I want. If I want tau yx, really what it is du x over dy plus duy over dx. Or if I wanted tau zy, just putting an arbitrary one out there, that would be du z over dx plus dux over dz. Oh, sorry, I wrote the wrong one. That would be zx, not zy. Apologize for that. So the shear stress actually involves two velocity gradients. The reason I didn't bring it up is because, at least for the very beginning of this course, actually for pretty much the entire course, the flows that we'll deal with will only have one relevant velocity gradient. So the equation will just simplify down to one velocity gradient. When I had our Coop flow that looked like this, where this is the y direction and that's the x direction, the uy here is 0. There's no vertical velocity. And so in the shear stress term, the duy dx term would just be 0. It doesn't show up. And we get back to our original expression. But I just wanted you to be aware that the shear stress is actually a little more complicated than what we started with here. But it really won't be a factor in most of the work that we do. And then the very last item that I'll mention is, once we have shear stresses, we can calculate shear forces. And since the shear stress can vary from point to point, it's best to write this in terms of differential quantities. So a little bit of shear force would be like the shear stress times a little bit of area, right? If we have some big surface here, let's say a big plate, and we have some shear stresses acting over it, maybe the shear stresses vary from point to point. So to find the shear force on that little bit of area, dA, let me redraw the shear stress. Let's say the shear stress there is tau. Then the little bit of shear force on that area, let me draw that in a little, oops, I'm just having a terrible time. Let me draw the shear force in a different color here. So the shear force here would be just our tau times dA, right? So it's just the shear stress times a little bit of area. It's kind of like what we did, it's actually exactly like what we did for hydrostatic pressure forces. To find the total pressure force on a surface, what we did is we broke the whole area up into little bits of area, multiply that little bit of area times the pressure to get the pressure force on that small bit of area, and then added it up over the whole surface. Same thing with viscous forces or shear forces. We break up a big area into small little bits, find the shear force on that small bit, which would be the shear stress times that little bit of area. We add it up over the whole thing. So our total shear force would be adding up tau times dA. Now it gets a little more complicated here because you just have to, again, watch out for the directions of the shear stresses and such to make sure you get the orientation correct. Okay. All right. We've come to the end. Take a look at the examples as usual, and let me know if you have any questions.